Oh, hey there, everybody. Didn't notice you standing there. My name's John Linick. I'll be your host and tour guide through today's session. Oh, hi. How are we doing today? As you know, I'm not Ed. So Ed actually had a medical thing, so we were basically taking turns filling in for his class. So I'm basically pretending that I'm Ed today. Thanks, Anthony. I try to be silly whenever possible. But exactly as Eli says, we're all kind of teaching today, taking a bunch of turns. Whenever problems happen, we just fill in and do what we need to do. And so I'm actually really excited to be teaching this class, though. It might be, well, I don't know if it's my favorite, I would say, but acids and bases in general is one of my favorite concepts that shows up in the Gen Chem section. So this is a pretty huge one. We cover a lot of really major ideas. I also highly recommend you all, after this class, to either watch the Acid Bases 2 on archives or the next time that it's offered. I don't know if Liz knows when it's happening next, but definitely kind of do it in terms of like pairs. They really do follow each other quite well. Cool, thanks, Liz. She'll let us know when the next one's happening. In the meantime, as you know, same party as before. We got the same crew of teachers that have been here all day, so if you have any questions, definitely let us know. Both Liz and Pat and Eli are rolling with the public and the private chat, so if you have questions, do not hesitate to let us know. Exactly, same MCAT party. As you guys know, we try, right? I mean, you're sitting in front of your computer at potentially 9 o'clock at night learning science. Like, it better be fun, right, Valerie? All right, so we'll try to jump through. We have a lot of stuff to cover today, but a lot of it, we don't cover too much ground, to be totally honest. We spend a lot of different ways, examples or types of ways to approach the same concept, and a lot of it kind of falls back in this main category of acid and base strength. Thanks, Anthony. We made ourselves jerseys even. All right, so after that, we'll talk about gram equivalent weight normality. I know a lot of people really do not like the idea of normality, so we're going to hit that pretty strong today near the end of class. And then we'll also go through a little bit about titrations at the very end. One thing as a heads up, though, the acid bases 2 is the one that really gets into titrations and spends most of the time really going through that. So heads up, we do titrations pretty briefly today. Most of it's in acid-base strength and things like calculating pH of a solution, relative strength of acids and bases, and all that kind of stuff. Should be pretty fun. All right, so let's just jump right in and get this party started. Before we even talk about acids and bases, there is another thing I want to discuss, this letter K. In fact, what does that K really represent? I might draw a little thing here. I don't know if anyone's actually, I've drawn this I think once before in a class, so you might have seen this before. You got it, equilibrium. Tell me more though. There's a lot of different things that you can actually say about that equilibrium. So it's a giant K. You can see that I'm actually giving it leads. There's going to be a point to the madness soon. It is dependent on temperature, George. That is a very major point. I'm glad you said that. So the only way you can ever change the value of K is by changing the temperature. Memorize that point. So that's whether it's KEQ, KSP, KA, KB. Like that is one of the really big ones. I'm glad you said it. So let's see, a couple other big ones there. The rate of the forward reaction equals the rate of the reverse reaction. Ayla, exactly true. That's totally correct as well. So that's true whether it's also KA, KB, KAEQ, K, whatever you want it to be. And so now, why do you think that I drew this K tree, as Eli is naming it as it is? Where do you think this K tree looks like it is, given how it's drawn? You got it. It's on the beach. It's in paradise. Hawaii. I like it. It's good fun. You got it. So the reason that I'm drawing this big K tree as an island paradise is because I want you to, whenever you see the letter K, whether it's KEQ, KA, KW, all of the Ks, KSP is the other big one, think of this tree, because no matter what reaction you're talking about, whether it's Ka or B for acid-base chemistry, or KEQ for normal reactions, KSP for solubility, it's where the thing wants to go to. This is paradise. It's where it wants to be. And so I also like to draw this with a little guy here. You might notice that he's smoking a stogie. The reason that he's smoking a stogie is because if you look at his head there, can you tell what his head looks like? Oh, hey, notice his head is a letter. It's the letter Q, Sheldon, exactly true, because here's the thing. Q describes wherever the point in the reaction is. We call this ion product and solubility. We call it Q in our reactions. But the Q is you. It's where you are at any moment in time. And what I want you guys to be aware of is that sometimes it's under the K tree. You know, you could have a reaction that's equal to K, but it doesn't have to be. Sometimes you're far away from it. Sometimes you're closer. Sometimes you're heading there. Sometimes you're being blown off course and blown away from it. But exactly, like, do be aware this is paradise, and Q that's the example we see in KEQ type reactions most of the time. It could be equal to K, but it doesn't have to be. All right, so hopefully this image is burned into your brain. You will think of it for every K thing. There are a couple other concepts that we didn't mention yet. So we said K can be changed by temperature. George brought that up. That's major. What are some other big ones too? Long-term memory, perfect. There's something it doesn't include. Doesn't include. Well, it's true. It's an equilibrium, not a kinetics thing, George. That's totally true. So yeah, it doesn't describe kinetics. I agree. This is an equilibrium concept, which is very different than a kinetics concept. I'm just thinking structurally in the equation. So the equation always equals what over what. What do you include? What do you not include? Let's get kind of mathy about it. So it doesn't include solids. You got Valerie. It also does not include. And there we go. Rubini's got the equation. It doesn't include liquids either. And you got the formula for every K, no matter what K it is. K is always equal to, actually let's make this a darker color so it stands out really well. K is equal to the concentration of your products divided by the concentration of your reactants. This is true for every single K, whether it's Ka, Kb, K whatever it is, doesn't matter. It's always products over reactants. So this is reactants, we can read it. Cool, perfect, you got it. And also it's raised to their coefficients, Alicia, as well. That is totally true. So for example, if you had like A turned into B plus 2 C's, your formula for K for that reaction would be equal to the concentration of B times the concentration of C squared, and this is Alicia's bringing up, that is exactly correct, divided by the concentration of A. Now, the cool thing, though, and I know this would be a complicated K term to actually solve for, is that whenever you're dealing with acids or bases, it actually works out to be pretty darn easy and actually pretty darn perfect. And so I'm going to erase all this. Actually, you know what? I'll minimize the K tree. So if anyone wants it later on, we can just make it big. But what is the formula for every single acid-base question that you will always see? It's always the exact same, tiny little K tree. All acids have the exact same reaction. That's the cool thing. So it's always products of reactants, exactly true, but what is the products of every acid dissociation? We'll get to that soon, Esther. That's a good point as well. There we go, Ayelet, exactly. So every acid, like the reactions that acids do, and this is true whether it's polyprotic, triprotic, all that kind of stuff. This is the same thing we do every single time. Your reaction for an acid-base dissociation constant, thus Ka, is always equal to whatever your protonated version of the acid is going to be equal to the, sorry, it's going to turn into, I guess we could say first and foremost, protons plus your conjugate base. Now, I'm going to use the word conjugate a bunch today. You can call it the conjugate base. You can call it the conjugate acid. The thing is, they're conjugate pairs. So whenever you say conjugate, doesn't matter what it is. It just refers to the other version. Like, I'm just going to call them conjugates because I know a lot of people get kind of worked up about that. So that means every single Ka that you ever solve for, Ka is always going to be equal to two things. And actually, there we go. It's got it there, and it's got the same thing. And this is specifically Bronsted-Lowry, George. That's true, but that's the only. If we're doing Gen Chem, we don't really use the formula talking about Lewis acids and bases. But if you want to talk more about Lewis acids and Lewis bases, please hit us up in the Q&A. That's more the orgo kind of side of things, where we talk about nucleophiles and electrophiles. That we talk about acid bases or Lewis acids and Lewis bases. But hit us up. We could talk about that stuff for days too. So we will stick to more general Bronsted-Lowry definition today, or even more so, you could say the Arrhenius as well. Very similar terms. But this is what your formula is going to be every single time. So now the cool thing is, whenever we actually solve for this, what's the top term work out to be? So Ka equals products, which is protons and conjugate base. You've got it, Alex, just x squared. So all of your Ka formulas for every single acid that we're going to talk about actual proton dissociation, which is all we do today, is equal to x squared divided by the concentration of whatever that acid was. Now, if we're going to talk about that Ka term, what would a big Ka, like a very large Ka number, represent? Would that be strong or weak? Strong, exactly. So, I mean, just looking at the relationships here, if you talk about having a very, very high value of K, it means you have a lot of protons. And so the stronger the acid is, of course, the more protons it's going to give off. And exactly, George, larger than 1. We'll go through the strong acids today for the MCAT because there's only 7 technically strong acids that we'll discuss today, but we'll go through that in a second. All right, so that's this formula. That will be every single acid base, at least in terms of the standard, proton dissociation acids that we talked about today. And bases work out the exact same way. What would be the big difference for bases, though, that would make this different? Instead, one thing will be changed primarily. Yeah, it would just be OHs instead. So it's the same idea. It's just that instead of having H plus, you'll have OHs, and instead of having A minus, you'll have a conjugate acid. But it's the same thing. It still solves to being x squared over the concentration of whatever it is, and that equals either Ka or Kb. But it's the same thing, exactly. Just we'd be solving for hydroxides instead. Cool. Exactly. Same thing, Esther. High Kb means strong base, such as high Ka means strong acid. It's the exact same relationship. Totally correct. All right, so that's the general form of all the things we're going to be talking about. So you got to know this, because we will be using this quite a bit, especially in the acid basis 2 class. But let's kind of get through the idea of strength here. So for example, what is the name of this acid? You actually need to know this one. It does have a common name. It's acetic acid, exactly. Ethanoic acid would be your proper name, but yeah, acetic acid is pretty much the only way you see it written. And so its Ka is 10 to the negative fifth. So it's actually a pretty weak acid. Which, here's the thing, most acids are weak acids. There's only 7 strong acids, and we'll hit those today, but this is a fairly weak acid. How about this guy right here? It's a very strong acid. This is one of the 7. It's hydrochloric acid, exactly true. Notice that its Ka is very, very large, 10 to the positive 8th. We said if it's greater than 1, it's strong. Holy crap, this thing is super strong. Cool. They are meant to be, yeah, it's supposed to be back and forth. You got it. It's as you can see, it's a little typo, but one of those should be switched. Totally true, Eve. Perfect. So now, it's true, exactly. So this would be our, actually, here's one thing. Which one of these is an organic acid? Top or bottom? Which one's organic? Yeah, top is organic. Remember, organic just means it's made of carbon. So any carboxylic acid at all will be an organic acid, whereas any of your halogen acids are inorganic. So like HCl, HI, HF, all that other kind of stuff is an inorganic acid. Cool. We'll talk about conjugates in a second. So then base strength, Kb, this is your, here's a neat trick we could go through. So notice, what is the conjugate base of acetic acid, or sorry, well, I'll go through ethanoic acid. Or yeah, you go, exactly, it's acetate. You got it. So acetic acid, ic acid forms the acetate ion. In fact, this is always true. Any ic acid always forms an ate ion. Conversely, you might know the other type of acid, which is your us acids. All of your us acids will form what kind of ion for a conjugate base? Ite, you got it. So that would be your ite ion. Also, we can go even further and really kind of categorize these things. The ic acids are more oxidized. The ite acids are less oxidized. It's more oxidized, and the us acids are less oxidized. So general naming thing. Yeah, there we go, George. I like that mnemonic as well. I ate something, and it made me go ick, or it's icky. You got it. So ates and icks are associated, and the ites and us are associated. The cheesy little mnemonic for that, I always like to say, you want to know about us? It's cool. We're ite. You know, we're all right. Us. We're all right. Yeah, thanks. Yeah. Nerd alert. Okay, so with that covered, let's, yeah, I was gonna say super cheesy. Let's talk a little bit about the Kb here. And so I just want to warn you, this is a very common misconception, so not to give you a hint off the bat, but what would you expect? If acetic acid is a weak acid, what's its conjugate base? It is weak. I like that most people are actually saying weak, because it is a super common misconception where people say that weak acids have strong conjugate bases. So let's actually talk about the relationship and how we can solve this and kind of figure it all out. They're both weak. Yeah, you got it. Man, Lauren, so many people learn this incorrectly in college, it's not even funny. I've done polls before in classes where it's like 90% of the class is saying that, you know, weak acids have strong conjugate bases, but it's actually not the case at all. But it's, yeah, that's a common college issue. But so here's the reason why, and this is what we're going to talk about today. It's not memorizing, you know, this is weak, this is strong. It's thinking about reactivity. So if something is strong, that means that it wants to react. And if we're talking about a strong acid, the reaction that acids do, we've already talked about, it's giving off a proton, right? So then what would the action of a strong base do, given the definitions we've done so far? So strong acids, their reaction is give off a proton. So if it's a strong acid, every single molecule is going to give off protons. Yeah, you got it, Alex. So then you got it, Lauren. So in this context, at least for our Gen Chem standard definition, a strong base is going to physically rip off protons off of anything it can and make sure that it is protonated. You got it. Every single molecule, if it's a strong base, will remove a proton. So now here's the thing. Why is this weak then? Why is that not strong? Like in a more organic chemistry side of things, what makes that weak, thus stable, thus non-reactive, thus you could call it chill, you can call it a bunch of things, but why is it non-reactive? And there we go, Eve. The funny thing is, if you are ever asked an organic chemistry question, just guess resonance and you'll be right about at least half the time. But the correct answer is resonance, as we would expect for organic chemistry questions, because of, as you can see, you've got two double bonds there, and the negative charge can resonate back and forth, thus stabilize it. That's funny, but it's so for true shell. All the time, resonance is the right answer. Yeah, you got it. So basically spreads out, and here's the idea. The more you can delocalize and spread out charge, the more stable things are, thus the less reactive things are as well. So that's why acetate's actually a pretty darn weak acid. Oh, sorry, acetate is, yeah, a weak base, excuse me, just as acetic acid is a weak acid. So it works out the same. So this guy, on the other hand, that's a very, very, very strong base. And so NH2 minus is going to react with anything it can find. It's going to rip off a proton. Notice how freakishly strong this thing is. Even compared to like how strong hydrochloric acid is, this thing's freakishly strong. So let's go back to what I said it a second ago. It was a really good, it said inert. That was the word I was looking for. I forgot it. It was a second ago, but it was very impressive. Whoever said inert earlier, props. Let's talk about the conjugates to these guys here. And so in order to talk about the conjugates to those there, I first want to talk about KW. And so what is KW? Delete this stuff. Or make some space. I'm actually going to delete the K tree because it's slowing down the room. You got it. So it's water dissociation's constant. It's the auto-ionization of water. And so the cool thing is, if you take any acid and its own conjugate base, notice that if you actually stack up these reactions, both the acids and the conjugates cancel out. And so the net ionic equation of any acid and its own conjugate base, or any base and its own conjugate acid, will be just water. And water dissociates by itself automatically at a rate of, as you can see, 10 to the negative 14th power. Now, why is this number something you should actually recognize? Yeah, so it's if you take any acid and its own conjugate base, the net ionic equation is just water. Because notice how everything cancels out but water auto-ionizing. Gotcha. So yeah, why should this number look familiar though, everybody? 10 to the negative 14th. Yeah, Anthony, right? It's what the pH scale is out of, right? So the reason that the pH scale is out of 14, it's not an arbitrary number. It's defined as that because it's a property of water itself. So just as Anthony says, any pH plus any pOH equals 14, any Ka times any Kb, as Nava saying up top right there, is going to be equal to Kw. And so the cool thing is, if you know the Ka of acetic acid, you can solve for the Kb of acetate. And so let's do that. If we know acetic acid has a Ka of 10 to the negative 5th, what is acetate's conjugate base is Kb? Nice, Anthony. There you go. Esther, exactly. It's 10 to the negative 9th. So it'd be equal to 10 to the negative 9th. You need to be very comfortable working with your exponents like this. It's honestly super important, very, very common. And so remember, whenever you're multiplying exponents, you just add them. If you divide exponents, you subtract them. So this would be a common example of that. Negative 5 plus negative 9 gives you negative 14. Cool. So there we go. We've got the top one right there. The conjugate base is 10 to the negative 9th. Let's do one more little just kind of scientific notation math example problem. Tell me about hydrochloric acid's conjugate base. So what is the Kb of the chloride ion there? Remember, no calculators on test day. Yeah, negligible. You got it. Basically nothing. And there you go, Anthony and Salma. It's negative 22. Thus, it is, as Esther says, inert. So here's the thing to be aware of, and this is the common misconception. We say, strong acids have weak conjugate bases. That's not even true. Strong acids do not have weak conjugate bases. Strong acids' conjugate bases are so freaking weak, they're inert. They don't even function as a base. Like, if you saw a chlorine ion in solution, would you call that a base? Cl minus, is that a base? at all? Is that going to react with water and pull off protons? No way. It's super stable. It's very relaxed. Like, it might be a nucleophile, that's true, but it is not going to function as a base whatsoever, ever. Like, it just won't do it. It's not possible. And that's why you, of course, call these inert, not weak. And that's the big language change that I'd like you all to do. So then, tell me about the conjugate base of NH2. Notice what the conjugate base of NH2 is. Common thing, right? It's very, that's the key. Ammonia is actually a weak base. And so if you talk about it as a conjugate acid, right, because in this context, NH2 is the base, this would be the conjugate acid, it is an inert acid. It does not function as an acid whatsoever. In fact, it's such an inert acid that it actually is a base. You got ammonia is a base. And so be aware of that. If you ever have a strong acid or strong base, its conjugate will be described as inert because it's incredibly stable, non-reactive. It's not going to do the reaction that we're telling it to do because ammonia will never give off a proton. It would rather accept a proton than give one off. So that's the kind of common misconception. And that's the big focus of today's class, and like this kind of definition and this general idea. So here's the thing, Alex. It'd be an inert acid because notice here we're defining it as the conjugate acid to a base. But it's not inert. Ammonia is a base. Like, it's a weak base by itself. But since in this context, you know, like the weak acid, strong base kind of definition as conjugates, yeah, it's an inert conjugate. You got it. But it is a base for sure. You will see it function as a base on the MCAT quite a bit. So yeah, good question. All right, so let's do some exponent math stuff, and then we're going to kind of pick up the pace and do some examples and stuff. But that really is the main focus for today's class. As you know, the title was strength. So that's kind of like the main thing we do today. All right, so I'm going to give you some numbers here. So notice this would be the conjugate base of sulfuric acid. So sulfuric acid is so strong that its conjugate base is not a base. In fact, it's even an acid, just like we said for ammonia, but now we're discussing with acids. So what is sulfate? Notice sulfuric acid forms a sulfate ion. What's its Kb? Nice, that's there exactly. It would be 10 to the negative 12th. You got it. Which is also pretty weak as well. That's a really low number, right? Also very weak. How about the next one? Phosphoric acid. Its Ka is about 10 to the negative 3rd. So its first conjugate base is Kbb, 10 to the negative 11th. You got it. Hydrofluoric acid is next. It's 10 to the negative 4th. Notice this is the only halogen acid that's weak, so its conjugate base is going to be 10 to the negative 10th. And then the last one's acetic acid. We already saw that one, so there's your numbers for the last one. So what I'm going to do is give you the list of the strong acids. So the strong acids are, why don't you guys just shout them out in the chat, actually. Tell me the strong acids, and I'll start typing them in. We got HCl already, totally true. We got actually not HF. HNO3, that's nitric acid, that's another good one. Sulfuric acid, H2SO4, good call. We've got nitric, we got sulfuric, we got HI, as well as HBr, good call. And then there's two other ones that people often forget. Let's see if anyone called it out yet. Actually, phosphoric's not technically strong, Rochelle. There we go, Jose, Valerie's got it. That is perchloric acid, that's HClO4, as well as chloric acid, which is HClO3. So that's perchloric acid and chloric acid. Actually, here's a little question then. So if chloric acid is HClO3, what would you expect the name of HClO2 to be? Not chloric acid, chlorous acid, right? Remember the ics are always more oxidized than the us's. So if we were to go further, these are not strong. I'll put them on the other side. But you could say HClO2 is known as chlorous acid. And then you could say further HClO with nothing, just HClO, what would that be called? If it's even less oxidized than chlorous acid. Hypochlorous, exactly true. So that'd be hypo, right? Hypo too little, us acid, you got it. And that's why perchloric is the most oxidized. I don't know why they removed the HY from hyperchloric acid, but you just call it perchloric. For some reason, the HY disappeared. But it's the same root as hyper and hypo. It's weird. I don't know where that went to. It's one of those chemistry things that it just disappeared somewhere in the past. But exactly. All right, so those are your strong acids. Know all those. They're all going to have a very weak to the point that they're inert conjugate bases for the ones that are right there at least. Cool. Yeah, exactly. Eli's got the recap for you. All right, so we can do the same thing real quick to just fill this in. So how about ammonium, just because this is very common? What would its conjugate base be? So if NH3 is 10 to the negative fifth, this guy would be, so that's ammonium, 10 to the negative ninth, there you go, and then of course cyanide would be 10 to the negative 11th. All right, so that's just your scientific notation math stuff. We're going to move on and do some one concept question, and then we're going to move on to talk about calculating pH and negative logs, and then we do titrations after that and call it quits. So thank you very much for snagging that. Do you want? I'll just cover this up. We don't need it right now. Please put your answers into this poll here. Thank you, Eli. I appreciate it. I will let you guys answer this. And if you have no idea, I want you to think about another molecule that would be very similar to this. And that will help. So quiz question, what is this similar to and why? You got it. Very similar to water. Why is it so similar to water using your periodic table? There we go, Anthony. It's in the same group, right? So that means in the same column. So I think you call these chalogens, right? They're like to the left of halogens. Is that right, Eli and Liz and everybody? And Pat? I think you call them chalogens. Yeah, chalogens. We almost never use that word, but it's in the same group as sulfur and oxygen. They're right on top of each other. I always was, yeah, it's, so let's talk about it, Alex. So what makes, I'll draw water real quick. So what makes H2S primarily different than H2O? Like what's the one thing that we know is going to be totally different between these two? Well, this guy, hydrogen bonds, that's true. So water, hydrogen bonds. But what else? Let's think of the actual structure. Because remember, we're talking about this in terms of acids, right, and strengths. So it's bigger, right, Brett? It's a larger molecule. And so if sulfur is a larger molecule, tell me about those bonds to hydrogen. Longer bonds or shorter bonds? And O is also more electronegative. That's Y too, Anthony. Totally true. So sulfur is going to have longer bonds, right? So it's basically a bigger atom, so the bonds between them is going to be longer. This is the exact same reason why. If you think of all the acids, we talked about HI being a very strong acid, right? Then we said Br, Cl, all that stuff. HF has the shortest bond. This is why HF is actually the only weak acid of halogens, because it has the shortest bond. The shorter the bond is, what does that mean? Stronger or weaker? The shorter the bond is. The shorter the bond is, the stronger it is, the tighter the hold, right? Which means, in terms of acid, if you have a strong, short bond, is it going to be a better acid or a worse acid at getting rid of that proton? You got it, Valerie. It's going to be way weaker. It's less likely to get go because it's basically held on super tight. And so that's why HF is actually a very, very weak acid. Well, not very, very weak, but it's really weak compared to the other halogens. It's not because it's not electronegative. It is. It's that it's got such a short bond. It's too strong. It can't let go of it. In fact, to do a little example to real life, I don't know if you guys have seen Breaking Bad before. Anyone watched Breaking Bad before? I'm not going to give away anything if you haven't seen it. But so in the very early, it's like in the first episode almost, they use HF for a specific purpose, a disgusting purpose. They use it to get rid of bodies. They actually, they put bodies in a bathtub and dissolve them, basically using HF. So now here's the thing. If HF is the weak one, why would you use this to get rid of bodies and not a strong acid? And it actually makes perfect sense in an MCAT context. If you think about the properties, periodic table, all that kind of stuff, and membrane transport. So it's not just the tub itself. So the thing is, there we go, Bailey. Notice that it's weak. And if it's weak, it means that it's not going to deprotonate. And if it doesn't deprotonate, what kind of charge does it have, first and foremost? If it doesn't deprotonate, it is still neutral. So number one, it would be neutral because it's not dissociating yet, right? It's a weaker acid, so it's holding onto its proton, so it's neutral. And then additionally, it's tiny. And what do we know about tiny neutral things and membranes, biological membranes? They can move through the membrane. So this is what makes hydrofluoric acid so terrifying. It doesn't burn your skin and burn inwards. It gets into your membranes and then burns you from the inside out. Horrifying. In fact, if you look at HF burns on the internet, it's very horrifying. But the problem is if you spill some on your hand and then instantly wash it off with a weak base, it doesn't matter. The second the stuff hits your hand, some of it gets under your skin, and hours later, bubbly blister things start to form. It's really horrifying stuff. And so that's why it's one of the most disgusting, horrible acids to stay away from, because it is, yeah, internal combustion. But notice it's MCAT stuff, right? Membrane transport, ionic radius, all that kind of stuff. Totally legit. You got it. We do use them in labs. It's very, 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 very dangerous. It's hard to get lots of it. That's why they used it in Breaking Bad, because it's so difficult to get the amount you need to dissolve a body that it's impractical for anyone to do so. It's better to, I'm not going to talk about disposing of bodies, but that's the whole idea. All right. So yeah, I agree. There's no way a high school would have that. No way ever. Impossible. That's why they did stuff like that in that show. All right. So here's the thing. Now, using this same information, let's apply it to this question. What's going to be the stronger acid, HS or H2S or H2O? Which one's stronger? See, I'd love to give you context to remember this stuff in. That's what it's all about. If you can remember it, not just as memorizing for the MCAT, you will be so much better off on test day. So because of that, water is a weaker acid, H2S is a stronger acid, and what do we know about the ionization constant of H2O? It is, H2O's is 1 times 10 to the negative 14th power. So we know this will at least be greater than 1 times 10 to the negative 14th power, which means what can we eliminate? You got it. Definitely get rid of D. Definitely get rid of C, because that would be a very strong acid. And you could also get rid of A, because it's not going to be near 0. It's greater than 10 to the negative 14th, but it's still pretty darn similar because it's still the same Chalagan group. So it'll be probably something like 10 to the negative 10th, maybe, or 9, or 8, or 7, or 6. Doesn't matter. The entire category between negative 14th and 1 is the same answer. It's answer choice D. Sorry, B, excuse me, not D, B. As we have it all crossed out. You got it. So it is answer choice B. It will be much less than 1 because it's stronger than water, but it is not that much stronger than water. And so that eliminates everything but 1. Cool. All right, let's kind of change gears. Let's do more math. I know we have a bunch of math questions that people have been wanting to talk about in the Q&A, so let's kind of dive into it and get deep. Let's talk about negative logs. And so I'm going to give you some examples here. But what is the log of 100 equal to? Yeah, you got it, Lauren. 2. You got it. How about the log of 1 times 10 to the negative 6th power? What would that be equal to? That would just be negative 6. How about the log of 1 times 10 to the positive 6th power? If I get rid of this 6 here. There we go, get rid of it. That would just be positive 6, exactly true. So now here's the cool thing. Whenever we deal with pHs, where P just means negative log. So as you can see, pH means negative log of H. So the negative log of something like 1 times 10 to the negative 1th, which we have right here, would be what? If it's the negative log of 1 times 10 to the negative 1, the negatives cancel out and you're left with just 1. You got it. So then what if you had a concentration of protons, this is impossible for the MCAT, of 1 times 10 to the positive 8th? That would be negative 8, exactly. Super, super, super acidic. Now notice this works for pHs, this works for pKa's, it works for pKb's, it works for P of anything. Like, it really doesn't matter. Just P means negative log. It works for all these things. All right, so now this is where people start to get a little bit confused. Is when you're like, okay, well, I can take the negative log of 1 times 10 to the negative 6th. It's 6. But what if it's more like 6.4 times 10 to the negative 3rd? This is where things get a little bit confusing. And so here is the ninja trick, Lauren, exactly true. A times 10 to the negative b will be our standard formula here. And so all you have to do to get the answer is you take your exponent. Notice it's not the negative of the exponent. Like, drop the negative sign, because on the MCAT, every exponent you're going to see is negative. And so we only do this for negative, exponents, because it's all we see. So exponent minus 1, and then 10 minus your coefficient or mantissa. It's called both. Which in this case means we have 3 minus 1, because the exponent is negative 3. So 3 minus 1, decimal, and then 10 minus 6.4, I'll just say 6, which gives you about a 2.4. Exactly true. Pretty sweet, right? Now the thing is, this is an estimate. This is an approximate. This is not the exact answer. If you have a calculator, it's going to be a different number. But for the MCAT, this will always be close enough that you need. Yeah, it's a little bit. Well, I don't get into it, Esther. It's the actual halfway point is at 3.5. So like 3.5 times 10 to the negative 6th would actually be 5.5. But you don't need to really worry about that too much at all. And yeah, there's a bunch of ways you can do it. For the MCAT, you're going to be close enough. Don't even worry about it. You'll be good to go. Cool. Let's do some more. So how about the next one? I'm going to squish this a little bit, and they really do know you have no calculator, so they expect a lot of approximations. Yeah, there we go, 2 to 5%, so perfect, 7.8. So 8 minus 1 gives you a 7, 10 minus 2 gives you 8. You guys are rocking it. That is exactly correct. Now, this is why I like this class, because everyone, not everyone, but like we get pretty comfortable doing it this way, fine. Where people get confused is going backwards, where how do you take this pKa or pH and turn it back into concentration of protons? This is where people get confused. So the way that I recommend doing this, and I know this takes a second, but I really recommend on test day, write this out. Like CRC, just write down the trick. If you write down the ninja trick, you know, it'll make it easier. Then all we do is write down the numbers. So we know this is going to work out to be 13.3. So then what must B have been in order to get 13.3? B must have been 14. Awesome. So our exponent, whatever it is going to be 14. That's your negative 14 right there. And then what must A have been to give you a 3? Because 10 minus what gives you 3? A 7. You got it. So that means that your coefficient, or mantissa, if you want to use the fancy word for it, is 7. So then you'll have 7 times 10 to the negative 14th power. I know it takes extra time to write out the little trick, but if there's one place I've seen people make tons of mistakes in pH stuff, this is really where it's at. It's the going backwards for this, and so it's just better to play it safe, write it out. It'll take you a total of 5 seconds, and just make sure you don't make any silly mistakes on the MCAT. This is kind of better to play it safe. All right, we'll do one more. If you guys want more examples of ninja tricks, feel free, like, put it in the Q&A, but when you do put it in the Q&A, say, hey, how about this? Is it equal to this? Don't just say, what about, 10 to the negative 2? Make sure you put it in both ways, you know what I mean? Just we can double check and make sure you're correct. But let's do the last one. So let me know, what's the answer to the final one from this example? And then we'll apply this in your acid-base 2 class a lot. Whole lot. So looks like, remember, so this last one here, we're going to convert it back into an exponent. So if we're going to plug in the numbers, looks like it's going to result in a 1.8. So we know your B must have been 2, because it'd be 2 minus 1. Gotcha, yeah, that makes sense. A lot of people are saying the opposite thing. And then A, in order to get an 8, must have also been a 2. So you got it. It will be 2 times 10 to the negative 2, as lots of people are saying in the chat. Nice work. Cool. All right, so please, if you want more of these, we could do more. For the sake of time, I'm not going to do more right here. But do let us know. This is we like to call it the ninja trick, or there's a couple different names for it, the pH trick. But that is the way that it works. Take a screenshot if you haven't already written it down. But we will be applying it later on, and especially in your next acid basis class. All right, so we'll do this question, then we'll move on to the last portion of class, which is all titrations. I'll clear out. Oh, that's actually already clear. So put your answers into the poll. Take about 30 seconds to think about it. So there are 2 answers we're getting not many votes for. Any guesses what those 2 are? Yeah, the middle guys, right? So no one's going for answer choice. Well, we're getting the least votes, at least for B and D, because they're looking for the strongest base. So we either want the highest or the lowest. So we're getting mostly split between these 2. Now, one thing you got to notice here, this is the pKa of the ammonium ion. So they're giving you the pKa of the what here? Totally agree, Alex. Yeah, that's what it's all about. On test day, just if you need to, just limit it down to 2 and go from there. You got it. So this is the conjugate acid, right? So if you have a high pKa of your conjugate, well, how about this first of all? What does a high pKa mean? Does that mean strong base or weak base if it's a high pKa? That means weak, right? Just like having a high pH means not many protons, having a high pKa means a pretty weak base, or weak acid as well, excuse me. So yeah, sorry, since we said pKa, we're talking about acids, but you got it. So high pKa means weak acid. So if you have a weak conjugate acid, does that mean it's a stronger conjugate base or a weaker conjugate base? Remember, the weaker the conjugate base is, the stronger the acid, or conversely, the stronger the conjugate base is, the weaker the conjugate acid, right? You have this inverse relationship, right? So much to the point that if you have a strong acid or a strong base, its conjugate is so weak it's inert, right? So yeah, remember once again, so the stronger the conjugate acid is, the weaker the conjugate base is. So let's show it out on the screen. So in all of these pKa's of the ammonium ion, you can actually solve for the pKb of the actual base. So if your pKa is 9.26, what would the pKb of the conjugate base be? Or what's the formula you'd use to solve for it? There we go, just 14 minus it, exactly true. So notice the relation, this is the relationship that people are kind of asking for here. Notice that the higher the conjugate acid's pKa is, the lower the conjugate base's pKb is. Is that making sense now, people who wanted a little bit of written out? Conversely, if you've got the lowest pKa of your conjugate acid, that means you've got the highest pKb of your conjugate base. But since we're dealing with p's here, what means stronger? Higher pKa or pKb, or lower pKa or pKb? What's the strongest? Higher numbers or lower numbers? The lower numbers, exactly. Which means, and you can see it in the chat there in terms of the poll, excuse me, most people are saying C. C is the correct answer because it has the lowest pKb. No, weak will pretty much always be weak, Anthony. I guess the general theme is, though, the stronger the conjugate base is, the weaker the conjugate acid is, and vice versa. You know what I mean? So, like, it's always a relative because no matter what, if you add the pKa and pKb together, it's always going to give you 14. That's kind of like the trick to that. Cool. And that's why if you have something like, you know, like, oh man, like a strong acid like hydrochloric acid, in order, the pKb of chlorine is basically negligible. It's almost nothing. Oh, and also a couple questions for screenshots on a Macintosh. All you do for a screenshot is Command-Shift-4. It'll give you a little crosshair, and then you can click and drag and take a picture. So Command-Shift-4 gives you crosshairs to take a picture if you got a Mac as well. Cool. Cool. Yeah, Sheldon's exactly correct. So read what Sheldon there. The lower the pKa, the stronger the acid is, right? Same thing for B. The lower the pKb, the stronger the base is. So just generally speaking, the lower the P number, the stronger it is. Just as having a very low pH means a very strong, lots of protons, right? And exactly as Russell says, pKa and pKb will always be inverse. Cool. Cool, there we go. Okay, there we go. Okay, I think everything's kind of coming together now. All right, let us know if you have questions. That was a lot. We kind of blew up a little bit in the Q&A there. Exactly. Cool. Yeah, it's Rochelle. That's the thing. Though we can use the. I mean, you can call it a conjugate acid or a conjugate base, but the main thing is remember that they are conjugate pairs. That's the trick. So if you're going to talk about ammonia, its conjugate pair would be ammonium, right, and vice versa. All right. So lower the P number, the stronger it is, and the stronger the acid is, the weaker the conjugate base, and vice versa. Whew. All right, everyone's got it now. All right. So sorry, there's a little bit of confusion. I think we cleared it up. So what we'll do for the last part of class, let's talk about the whole like titration things, like the gram equivalence, weight normality, and all that kind of stuff. This is going to get more into actually neutralizing things. Cool. Yeah, you're totally right, Stacy. Just remember, the stronger the one is, the weaker the other is. That's really what we're getting at there. So I'm just saying stronger, like relatively stronger. The other one will be relatively weaker. But in all the MCAT stuff that we talk about, we pretty much, every weak acid has a weak conjugate base. Every weak base has a weak conjugate acid, because the only things that are strong, in fact, let's talk about this real quick. What makes something strong? Why do we have to assume to make it like strong? So that's what I'm using relative, stronger or weaker relative terms. 100% pure dissociation. So in order to call something technically a strong acid, you mean 100% of those molecules will get rid of the protons the second they hit water. Like boom, getting rid of all of them. Same thing with a very strong, if you call it a strong base, like defining it as a strong base, that means 100% of those bases will rip off protons from something once they hit the solution as well. Cool. Yeah, there we go. Stacey, you're totally correct. You got it, because we're looking for the strongest base. And let me know, Stacey, but you are totally correct with that. So yeah, all right. Okay, hit us up if you have questions. I'm going to run through this, though. But that was kind of... Oh, Alex has a good point. We will not talk about super acids on the MCAT. Technically, you can have acids that would have pHs of like -12, like legit negative pHs. Those are super acids. They're non-aqueous solutions. Don't stress about them for the MCAT. That's beyond the scope of what you need to know. If you want to geek out about them, Google it. Hit us up in Q&A. We can talk about them. But yeah, technically, you can have negative pHs. It's just you're not going to see it on test day because it's not biological, and the MCAT's largely biological now. So, all right, so let's talk about reacting equivalence, normality. This will be this, and then a little bit titration stuff will kind of be the end of it. So what equivalence is basically when we say one equivalent of acid. So one equivalent of acid means 1 mole of protons, 1 mole of H pluses. So notice if you got 1 mole of hydrochloric acid, well then you get 1 mole of protons because every molecule of hydrochloric acid has a single proton to it. Conversely, if you've got something like sulfuric acid, how many equivalents of protons do you have in 1 mole of sulfuric acid? 2. So it'd be 2 moles of sulfuric, 2 moles of protons, thus 2 equivalents of acid. How about like a base like this, calcium hydroxide? It would also be 2 equivalents of bases, right? Because it gives off 2 hydroxides. Now, you could also do other things too. Like, for example, if you've got 1 mole of, let's do phosphate, PO4 3-. So you got to know phosphate, very important. Bones, metabolism, everything like that. How many equivalents of bases would that be? Yeah, so this would be 3 equivalents of base. Why is it 3 equivalents of base? What's the hint that you know it's 3? Yeah, it's got a -3 charge. And since it has a -3 charge, that means it can pick up 3 protons. And so it can pull 3 protons out of solution and thus protonate itself, functioning as a base. You got it. All right, so that's the first thing, that's equivalence. That's going to come back full circle when we talk about normality. Next, we have gram equivalent weight. So this might look a little bit confusing, but I want you to know what gram equivalent weight is. It just means how many grams it takes to get an equivalent. That's all it means. How many grams it takes to get an equivalent. So for example, the molar mass of sodium hydroxide is 40 grams per mole. So that means the gram equivalent weight of sodium hydroxide is 40 grams. Because every mole you get 1 equivalent, so you would just call the gram equivalent weight 40, because it takes 40 grams to get an equivalent, or 1 mole of hydroxides. So now, if you've got something that's diprotic, like calcium carbonate, would you expect the gram equivalent weight to go upwards or downwards? Anthony's got it. Down. Why down? You divide it in half, that's exactly true. Why do you divide it by 2, though? Why not multiply by 2? Because, notice it takes... Exactly, there you go. You need less of it to get an equivalent, right? Because if you have 1 mole of sodium carbonate, that's what Na2CO3 is, that means you get 2 moles of hydroxides, right? And so if you want to solve for the number of grams it takes to get just 1 equivalent, well, then it would take half a mole to get 1 equivalent, because every mole gives you 2 equivalents. Exactly true. So that's what it is. So notice all we're doing here is when we're looking at gram equivalents, all you have to do is just divide by the number of either protons or hydroxides that it has. So if it's diprotic, divide by 2. If it's triprotic, divide by 3. If it's whatever it is, just, yeah, divide by the number. Cool, perfect. Good to hear, Anthony. So the last part of this puzzle then would be normality. Oh, yeah, totally. Oh my gosh, I never got any of this stuff in college. It wasn't until I started studying for the MCAT that I actually learned most of this. It's kind of fun. But so normality, last bit. So normality is just giving you equivalents per mole. Now, here's the funny thing about normality. All you do, it just means just now multiply by the number of equivalents. Equivalence, there we go. So for example, let's say that we have I'll give you another example with more normal numbers. Let's say that we have a 3 molar solution of phosphoric acid, H3PO4. So if you've got a 3 molar solution of phosphoric acid, H3PO4, what's the normality of that solution? You just multiply it by 3. So that would be a 9 normal solution. Exactly true. So whenever you're dealing with normality, all you have to do is multiply by the number of equivalents you have. Whenever you have gram equivalent weight, you just divide by the number of equivalents you have. Because normality is describing how many protons are already in solution. Gram equivalent weight is talking about how many grams it takes to get those equivalents in solution. Cool. And that works for everything. So like, what if you have a 2 molar solution of sulfate ion? So if you have a 2 molar solution of the sulfate ion, what's that normality? So 2 normal solution of sulfate would just be 4, right? Because sulfate's got a -2 charge, as we can see right here, which means, of course, you'd multiply the 2 molar by, whatever the charge is, because that's exactly, so it'd be 4. Perfect. You guys got it. All right, so what we're going to do now for the very last part of class is use these numbers to basically describe how to solve a bunch of stuff. And so this actually gets covered much more in depth in your acid bases 2 class. So I'm going to skip the whole idea of like equivalence point and why it's higher or lower today. Instead, I'm going to focus on the math because this is more in your acid bases 2. So what I do want you to notice is that whenever you have a vertical line here, this is known as the equivalence point. And so we get into the reason for the shape in the next class, so I won't do it today for the sake of time. But so what's true of the equivalence point? So the vertical line is your equivalence point. And it means that there you go, it's equivalents are equal. So moles of protons equals moles of hydroxides, or moles of acid equal moles of base. So moles acid equal moles base. So you've added an equal equivalence of acid and base. One thing I do want you to notice though, so notice regardless if you have a strong acid and strong base, or a weak acid and a strong base, it takes the exact same amount of base to neutralize it. Because if you're adding a strong base like sodium hydroxide, oh my gosh, it's going to pull protons off of anything regardless if it's weak or strong. So when you're solving for equivalence point, when you're actually solving for the numbers here, like how many moles, milligrams or moles, whatever it takes, we don't care if it's weak or strong. So now it does depend on, of course, you can see the equivalence point, pH will change, but we cover that more so in your next acid bases class. Today I'm going to focus just on the numbers here. All right, so here are the numbers and your various equations we have for all the different equivalence points. So the cool thing is every equation here, whether you take normality and volume equals normality times volume, every single equation gives you the exact same answer. It's moles of protons in solution are going to be equal to moles of the base in every single example. So if you want to take a screenshot of this, it's pretty much the stuff that we already saw, because notice if you take the mass of your base divided by gram equivalent weight. So remember we said gram equivalent weight is how many grams it takes to get a mole. So if you take the mass, divide by how many grams it takes to get a mole, you're left with how many moles. And so that'll leave you with however many protons or hydroxins you have. And yes, you can use all 3 of these to solve for equivalence point, Valerie. It's exactly true. All right, so screenshot. We're going to end by doing just a couple questions of this and kind of show how it works. All right, here we go. So using the equivalence point formula. So let me know what volume of a 10 to the -1 normal solution of sodium hydroxide will neutralize 40 milliliters of a 10 to the -1 same normal hydrochloric acid, also monoprotic? Yeah, Lauren, it's just going to take the exact same concentration. So the formula would be NAVA equals NBVB, thus moles equals moles. Turn around, solve for 40. The shortcut is, though, notice that if you got the same concentration, then it's going to be the same volume as well. So 40 milliliters of base will be neutralized by 40 milliliters of acid. Exactly. All right, so now what about the next one? If we have to solve for milligrams, remember we gave you on the previous page that sodium hydroxide is 40 grams per mole. Shelton, you got it. If it was diprotic, it would change things. You'd have to double it. Totally true. That's exactly correct. So remember this formula we would have. We've got one of these as solutions. We'll have our normality times our volume. The other one is mass divided by gram equivalent weight. Remember this is gram equivalent weight, which is equal to how many grams it takes to get a mole. or an equivalent. So we're solving for how many grams. What's the gram equivalent weight, though, of sodium hydroxide again? 40. So all we got to do is plug and chug, right? So we've got a 10 to the negative 1 molar solution times 40. And so then that equals whatever the mass is divided by 40, which leaves you with, Anthony, nice work, just 160 milligrams. Notice that we're disregarding milligrams. Why did it not convert milligrams to grams? Anyone notice why I just disregarded that? Yeah, they cancel, Lauren, because we're using milliliters and milligrams, so you can disregard the milli. All right. Last question of the day, doing this stuff as well. And remember, we do get really into all this stuff way more in acid bases too. So I actually taught that about a week or two ago. So if you want to check it out in the archives, it's right there. But let's do this last question for the day. We're doing the same thing as before. So mass divided by gram equivalent weight. So we said the gram equivalent weight of sodium hydroxide is 40. The gram equivalent weight of this KHP is what? Okay, it's 204, exactly. So that's just because the molar mass is 204. Now, what would happen if KHP was instead a diprotic weak acid? If it was diprotic, what would that do to your gram equivalent weight? Yeah, you divide it by 2, then it would be 102 exactly. Because if it's diprotic, it only takes half a mole to get a full mole of protons. So once we just set it up and plug and chug like before. So it's 408 milligrams divided by 204, and as Anthony, Lauren already said this in the chat, exactly true. That means it's going to take 80 milligrams, or 2 moles, or in this case millimoles, to fully neutralize your acid. All right. Nice work, everyone. I do implore you, check out either the upcoming Acid Bases 2 or check out the one on the archives. It really goes through a bunch of this stuff and gives you a lot more examples, and that's kind of the foundation of this point on. All right. You're very, very welcome, Bailey. Thanks for hanging out, and I know that was a really intense class. Hopefully we learned a lot. Stick around. We've got more channel coming up soon. I believe Eli's coming back on. All right. Take care, everybody.